Okay, good afternoon to all of you. Am I audible? Hello? Okay.
Yes, sir.
Okay, fine. Okay, so we'll be discussing about classification algorithms as today also. I think what we have done in last class is uh, the classification using decision tree algorithm, where we have discussed uh, decision tree algorithm methods like ID3, CART, and C4.5. Then we have discussed what is overfitting and then how this overfitting can be overcome through some pruning methods. So pre-pruning and post-pruning and all. So now we'll move to one of the important algorithm of classification that is known as Bayesian classification. Sometimes it is also referred as naive-Bayes classification. As name refers, that is actually a probabilistic method for a classification based on Bayes theorem, which is a famous algorithm, a famous method, a famous formula, conditional based on conditional probability. Okay, so let me go further. So it's a statistical classifier, predict class membership probabilities based on Bayes theorem. We referred it as naive Bayesian classifier. Since actually we actually do classification using Bayesian classification with some assumptions, which actually makes this particular algorithm computationally simple. Okay, so as far as performance, it is comparable with decision tree and neural network classifiers. There are two things which is very important. Now, first thing is this is referred as probabilistic learning, and the second one is it is incremental in nature. Uh, Certainly, when I say probabilistic learning means it actually uses explicit probabilities for hypothesis than among the most practical approaches to certain types of learning problems. Whereas incremental, that actually means that each training examples can incrementally increase or decrease the probability that a hypothesis is correct. Prior knowledge can be combined with observed data. The simple what we are doing is that suppose some unknown sample is there, and using Bayesian classification, then it is actually class. What you have is that you actually predict the class of this particular sample. Once class is known for this particular unknown sample, so this particular unknown sample becomes a part of the training data. That means we can actually include in the training samples, and certainly In result of that, what will happen? That all the probabilities which actually we have already calculated based on hypothesis and all will change. Certainly, in some cases it may increase, in some cases it may decrease as well. So that way it is incremental in nature. Okay, fine. Let us go for this is what we call it as Bayes theorem. This is very famous conditional probability based theorem. What it actually states that suppose let X be a some data sample whose class level is unknown. Let H be some hypothesis that X belongs to a class C. Okay. So remember, X is a data sample. That means when I say X is a data sample, that means I'm just talking about like this. Suppose you have data some suppose X. So X can be A1, A2, AN. That means what does it mean? That means I can put some values. Say A1 is name, so I can say Ram. A2 is age, so I can say 32. So income is 50,000 and so on. What? So this is your X data sample whose class level is unknown. So class I have to find for this. Now H be some hypothesis that X belongs to a class C. Since you know that in classification the labels are known, so suppose you have say Ci whether I equals to 1 to M. So there are M classes you look for. So H actually talks about that X belongs to a class C. Okay, so that means uh, unknown sample X belongs to say Cj. So this is what hypothesis we look for. Okay, so what you need to do is that you have to find out this. This means that X is given. What is the probability that this is true? Okay, that means your actually the aim, the objective of your actually this method is that your unknown sample is given. Unknown sample, if I say, that means class is not known. So this X is given, given X, and your hypothesis what you have is that H states that X belongs to a class C. That means this may be this H actually corresponds to C1 to Cn, any number of classes. So it is actually you have to find out whether it is C1x or PC2x and so on. So given X, what is the probability that it will fall in C1? What is the given X? What is the probability it will fall in C2? And so on. You have to find out all the probabilities. Okay, conditional probabilities, as I say. So this is what. So the PH by X is the probability that H holds given the observed data sample X. So this is referred as posterior probability of H conditioned on X. So always remember posterior probability of H conditioned on X. Now, this is one very famous example through which you can actually understand the Bayes theorem. What X is saying, X says that X is round and red. Now, H is that hypothesis that X is an apple. That means what I am saying is that there is an object which is round and red. Now my hypothesis is that X is an apple. So that means if I say that PH by X, that means given the object is round and red, what is the probability that it will be apple? This is my task. So PH by X is our confidence that X is an apple given that X is red, round and red. Okay, so this is what we are looking for. Now, certainly I'll be looking for PH, PX and all. PH is a prior probability of H. That is the probability that any given data sample is an apple, regardless of how it looks. Okay? So when I say PH, that means I'm looking for PC1, PC2, and PCA. So I'm just looking for what is the probability of class 1, class 2, class M. Okay? So this is known as prior probability. Okay? Always remember that when you look for prior probability PH, it will be always be independent of X. So, so now as Bayes theorem requires that what is Px by H? That means hypothesis is given. What is the probability that it will be? What is the probability of occurrence of X? It is the probability that X is round and red, given that we know that it is true that X is an apple. Okay. So here Px is prior probability, that is data sample from our set of fruits is red and round. This is the Bayes theorem states that given, like we have Px, Ph and Px by H may be estimated from the given data. So using Bayes theorem states that you have to find out the probability given X, what is the probability of occurrence of H, then it will be Px by H, Ph by Px. Okay, so what actually we will be doing it? We have to find out this. Obviously, Ph by X, Px is equals to Px by H, Ph. This is obviously either this can be optimized or this can be optimized. So your objective functions, like when you go for making objective function out of this, either you actually you make objective of this or this. Since certainly when you look for objectives, then certainly you have to see that what are known and what are given. So in that case, this I can calculate from the data, whereas this I need to know. So this is unknown. This is not known to me. Whereas this is known to me, this is known to me. That means that I can calculate from the data, that I can calculate. So what I can do is that I'll just optimize this part. So before going for the objective function, uh, there is one thing which assumptions we look for, which actually simplifies the computations as well. And that particular assumption is class conditional independence. So class conditional independence actually states that effect of an attribute values on a given class is independent of the values of other attributes. Okay. Actually, this actually ease into computations. The reason is that between the attributes there is no dependency factor involved. So that actually gives me some sort of simplification. So, what are the steps involved in this? Steps are that first step is data sample is of the type X, which is nothing but uh, Xi's, which that means there may be any number of features that particular samples will be. So we are assuming that it has n number of features, where Xi's are the values of X for attribute AI. That means when I say what that means, if I say that name, this is your AI, whereas Xi, if I say small xi, then the value, what is the name is Ram. So this way it goes like that. Now I'm assuming that there are m number of classes. So what you look for is that X belongs to Ci, that means X, the unknown sample X, belongs to class I if and only if P of Ci by x is greater than P Cj by x. Certainly, this j will move from 1 to m, and certainly j should not be equals to I. So what it Bayesian classification assigns x to class Ci having the highest posterior probability condition on x. That means what I'm looking for is simple. So it is something like this, that I am going for P C1 by x, then I'll be going for P C2 by x and P Cm by x. So I'll be calculating all these and the maximum will be. So the probability having the maximum will actually define that the particular sample will belongs to class C2. Suppose your maximum is PCR by X. That means the X sample belongs to class R. That is what we look for. So, we'll actually model this particular thing into a maximization function. So you can see that uh, this is my Bayes theorem in terms of class. So this Bayes theorem specifies Px is constant, only this need to be maximized. So what we have, since this is a constant, so it will not affect anything in this. So we'll be looking for maximizing this part. Okay, and this maximizing this will actually give me the result of this. So this can be like, so we what we have is this. Okay, so we maximize this. Suppose your class probabilities are same. The moment class probabilities are same, this goes off. Only this part maximization will give you the result. So in suppose you have a data, and while uh, applying this particular method, you found that all the class probabilities are same. So in that case, there is no need to compute the class probabilities and should be multiplied in the conditional probabilities of Px by Ci. Rather, Px by Ci itself will actually optimize the thing. So, uh, what we have is we'll be going for Px by Ci. So, as I told you that if assumptions will not take, then certainly this, if there is a dependency between attributes, then obviously computing Px by Ci is computationally expensive, and sometimes it becomes infeasible as well. So what we do is that we apply the what we call it as naive assumptions, that attribute independence, or whatever we have seen, that class conditional independence. So what it actually provides you, that the moment we assume this, what happens is that this, that Px by Ci can be seen in this way, and this can be seen in this way. That means individually given class, what is the probability of sample, this can be calculated and all are multiplied will give you this part. That actually gives you ease in computation. So in order to classify an unknown sample X, you have to evaluate this for each class Ci. So this is what the final function is. Okay. Any queries up to this, you can ask. Okay. So no queries. So I'm just moving forward. Let us take one example data. This is an example data where actually there are, you can see that there are attributes like this. So this is my A1, A2, A3, A4, and this is my C class. So how many class you have is 2. The C1 is yes, C2 is no. Suppose if I, so you have 2 classes in this. How many records you have? 1, 2, 3, 4, 6, 8, 10, 11, 12, 13, 14. So total number of record is 14. So what is the probability of class C1 and what is the probability of class C2? If you find out, then yes is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 by 14 and obviously rest is 5 by 14. So this is what prior probability you will be having. Okay. So since PC1 is not equals to PC2, so you will stick with the entire objective function, will not be reducing the objective function in this case. Now what you have is, let's suppose you have a sample this is your sample, and what is unknown is that class is not known. That means you have to find out. So what you have is, this is a1 value, so this is actually x1, x2, x3 and x4. So you have x1, x2, x3, x4. Okay, the values, and this x1 is corresponding to a1, then a2 is x2, a3 is x3, so a4 is x4. This is what we have. So we'll be looking for this. So once you calculate the class probabilities, prior probabilities, then it will be 0.643, and then 5 by 14 is 0.357. This we have. Now we'll be going for this. So this is actually this. Now what we have is that this is nothing but px by c, which is nothing but pxj by ci, where j is 1 to 4 and I is 1 to 2. This is what we have. So what you need to do is that you have to find out p x by c1, p x by c2, which is nothing but p x by c1 is nothing but p x by c1 into p x2 by c2, c1, then p x3 by c1 and p x4 by c1. So this is required to be calculated just to have px by c1. So we'll move it. So first of all, what we'll do is that we'll be finding out that age is less than or equals to 30. Let me tell you one thing, that when I say, okay, what I mean is that you can always see that this particular, this particular sample, the sample is not present in this data, that you always can verify. So when you look for such, okay, fine. So what we have is that uh, what we are looking for is, x is greater than 30, medium, yes, and fair. So just check that in any row whether there is a entry for this or not. That means all four values are actually creating a row in this data or not. If yes, certainly then and there whatever class label is there you can assign to this. But in this case, what is happening that this particular combination of instance is not present in this data. So that means this is unknown sample whose class is not known. So I'm just looking for finding out the class. Okay, fine. Okay. So first probability which you look for is this, that P less than equals to 30, that is age is less than equals to 30, and the class is yes. So we are looking for, what you look for is this, P age is less than equals to 30 and C1. This is C1 is nothing but yes. Now if you look that there are two instances of this, then there are instances like this and this. Okay, so there are five instances. 1, 2, 3, 4, 5. Now see that out of like how many instances what you have is yes. So this is yes, this is yes. Okay, so out of 9, only two instances which corresponds to this. So you can see that this is coming as 2 by 9. Fine. Similarly, if you go for less than equals to 30, where class is no, then you have to find out that how many. So you can find that these two are no. So there are two instances. So out of 5 no instances, 2 instances, the value is less than equals to 30. So you will be having, sorry, I think there are 3 instances. It's the third instance is 1, 2, 3. So it's just 3 by 5. Similarly, you can check for income also, medium and then class. So medium, what you have is, you have medium this, 2, 3, 4, 5, 6. There are 6 instances. Now check. There are yes, 1, no, there are 2, then there is 3, then there is 4, and there is no. So there are 4 instances of medium is yes. So out of 9, 4 is yes. Sorry, out of 9 yes, 4 is medium. So what you have is 4 by 9. So what we have is 4 by 9. Similarly, the rest will be, since 6 instances of medium is there. So if it is 4 by 9, then certainly the other one will be 2 by 5. So it is. Similarly, you can find out for a student also, which will be 6 by 9 and then 1 by 5. Similarly, you will be finding out for this part. So it will be this, this, this. Now, after finding out all these probabilities, then what you need to do is that you have to find out that if class is yes, what is the probability of occurrence of that sample? And that sample is actually nothing but it is a multiplication of the individual attribute probabilities, conditional probabilities. So which will means, so you will be multiplying with this, with this, with this, with this. And then in other one which is class is no, then you will be multiplying with this, with this, with this. So while doing that, you will be getting 0.044, and in case of class no, you will be getting 0.019. What it actually depicts is that this says that this is the probability that class is yes, then there is a, what is the probability that there is a sample x. So this actually gives you that part. Whereas in this case, this is the probability that class is no. What is the probability of the sample X? Now, since class probabilities are not same, so we'll be multiplying the class probabilities also. That means post-trial probability definition is actually given by two prior probabilities. So this will be added, so sorry, multiplied. So 0.044 into 0.643, this will give you 0.28, whereas this two will give you 0.07. Now compare these two. So what you get is this. Okay, so this is actually corresponding to the higher the maximum is this. So that means p x by y, py is greater than p x by n by pn. So this is what we have. So the unknown sample will belong to yes. So now unknown sample has class yes, which is nothing but C1. So this is what Bayesian classification talks about. So what we did is the moment you this unknown samples has a class this, I can add this to the okay. So what I was actually discussing is that finally when unknown samples has the class label, then that unknown samples may be added will be added in this particular data, and instead of 14 now instances will be 15. So all the probabilities will change because the class probability will be defined over 15 data samples for yes and no, and also and individual class also probabilities will get changed, and similarly all the probability will change. And actually, as you are adding on the data and training data is actually increasing in nature, then suddenly your prediction will become refined and refined. Okay. So any queries you can ask me regarding this method. Any queries? Okay. Okay, fine. The next algorithm, which is actually neural network based algorithm, which is known as classification by back propagation. Okay. As you know that this is a class of artificial neural network algorithm. Uh, Then the question comes, what is neural network? Let us see that what are advantages of the neural network and how what are the limitations of the neural network. Okay, so you can see prediction accuracy becomes high. It is robust in nature, works when training examples contain errors. Uh, Output may be discrete, real valued, or a vector of several discrete or real valued attributes. Fast evaluation of the learned target functions. So these are advantages which you get from neural network. The problem with the neural network is it has a very long training time, by sometimes like not from minutes to end. Sometimes it takes around 1 day also. Sometimes it takes maybe a week also, and depending upon the complexity of the neural network, it may go up beyond that also. Okay, not easy to incorporate the domain knowledge. So this is the input vector, this is the input vector, which is x. So you can have n number of features out of that. Then you assign the weights to all these. So there is a weight vector w, small w. Then you actually perform the weighted sum. Then you actually apply the activation functions, and then you get the output y. And also in between you actually have some bias and errors. So it's a n-dimensional input vector x is mapped into variable y by means of the scalar product and a non-linear function mapping. Okay, this is what particular neural network does. The objective of the training is that obtain a set of weights that makes almost all the tuple in the training data classified correctly. That means what you have is you actually when we actually try to train the network, then what we have is that you have given x. So input is with you at x returns inputs. Then you assign weights, and initially it is assigned as random manner. Okay? And then you try to adjust the weight. Why you are adjusting is that getting a set of weights or a set of optimized weight that actually makes the input sample to be classified correctly. Okay, so obviously in that is the goal of the thing. What are the steps? That you first initialize the weights with random values, then feed the input tuples into the network one by one. For each unit, you have to compute the net input to the unit as a linear combination of all the inputs to the unit. Then compute the output value using the activation functions. You have to compute the error as well, and then update the weights and the bias. Okay, so the all the related formula is this. So what you have is that you actually introduce the input vector. You actually introduce the input vector x size. So you have input nodes. Then there are hidden nodes. These black nodes are hidden one. Uh, there may be a possibility of one hidden layer, and there may be a possibility of more than hidden layer. Like in case of CNN, RNN, and all, there are many hidden layers possible. Okay. Obviously, always remember, as many hidden layers you will be introducing in the network, the entire methods become complex in nature. So more hidden layers, more complex. So more hidden layers, more complex will be. So training will take time in that case. Reason is very simple, that more weight calculations will be involved, more linear combinations will be generated, uh, error calculations, all these required for more number of nodes and more number of layers. So it will requires time for that. Formula The error formula is this, then weight, then input and all. So you actually operate the entire this particular multi-layer perceptron based on these formulas, and you optimize the weight so that the input samples can be classified correctly. Okay. What we'll do is that we'll solve the problems in tutorials so that you'll get the idea of all these formula, how it works, and how it actually this particular uh, multi-layer perceptron actually computes the class considering the input. Okay. Then comes what is network pruning and rule extraction. Network pruning is actually a fully connected network will be hard to articulate. So what we have is that there is n input nodes, h hidden nodes, and then m output nodes, which actually leads to h into m plus n weights. So this is what pruning says, that removes some of the links without affecting the classification accuracy of the network. Though it is not easy to do that, but there are methods available through which we can do that. Then the second one is that how to extract the rules from the trained network. So the first thing which you can do is discretize the activation values. So replace individual activation values by the cluster average, maintaining the network accuracy. Next is we can do that enumerate the output from the discretized activation values to find rules between activation values and output. Next, find the relationship between input and activation values and combine the above to have rules relating the output to input. So this way you can extract rules out of the trained network. I think this will be more clear when you will be solving the numericals. So in next tutorials, numericals will be solved based on this particular concepts, and you will be getting some more problems, some easy and difficult for your practice also. Okay. What are the other classification methods? The other classification methods are, say, k nearest neighbor classifier. We have case-based reasoning also. We have genetic algorithms. We have rough set approach, and then we have fuzzy set approaches. So all these also does the same thing. Is actually used as classifiers. I think all of these algorithms are well-known algorithms and widely used by different domain holders. So one by one, the KNN is actually approach which is actually based on instant-based learning. Okay. So what it does is it stores training examples and delay the processing. It is actually a lazy evaluation until a new instance must be classified. Okay. So in case of k nearest neighbor, what we do is that instances represented as points in Euclidean space, and for calculating the k nearest neighbor, we actually make use of Euclidean distance. Okay. There are other methods like locally weighted regressions, which actually constructs local approximations, whereas in case of case-based reasoning, uses symbolic representations and knowledge-based inference. Like one famous paper, which was actually uh, done by one of the researcher, and it was done for Cadet. Cadet is actually a company which produces or manufactures tap depending upon your requirement. So it is very much customized also. Okay, this is a famous, like this Cadet is a famous company of USA. So one of the researchers actually took this as a case study, and it actually shown that how this case-based reasoning could be performed for a better implementation of the tap or manufacturing. Okay. So let us first go for the k nearest neighbor. Uh, All instances corresponds to the point in n-dimensional space. The nearest neighbor are defined in terms of Euclidean distance, just I told you. The target functions could be discrete or real valued. So it can be both. So the for discrete value, the KNN returns the most common value among the k training examples nearest to x cube. So when I say that this is x cube, this is one some point you get. This is randomly you can pick this point, and then you look for k neighbors out of this. Whereas in this is one example of Voronoi diagram where this Voronoi boundaries are there, and you can apply one neural network. Sorry, one neighbor, nearest neighbor for training examples. Then how to deal with the continuous value? So in case of continuous value target functions, what you need to do is you have to find out the mean values of the k nearest neighbor, and distance weighted nearest neighbor. In that case, the weight the contribution of each of the k neighbors according to their distance to the query point x cube. So what you do is actually you are calculating the w, which is equivalent to 1 by distance between the xq and xi whole square. So what we do is actually uh, each of these points which actually referred as neighbors. So the distance calculations will be like this Euclidean distance you will be going for, and then the weight can be equivalent to this formula. Similarly, real value target functions can be dealt with. Uh, the advantage of this algorithm is it is very robust to noisy data because by averaging the k nearest neighbors, uh, there would actually what we call it as cost of dimensionality also distance between neighbors could be dominated by irrelevant attributes. Certainly, what we do is that to overcome with this particular problem, we do elimination of the least relevant attributes. Like we actually ignore which has least relevant in case of class level training. Okay. So next is case-based reasoning, which is again a Legio evaluation. Uh, it analyzes the similar instances that only the difference, like certainly what like k and n, it never uses Euclidean distance or Euclidean space. Uh, what they uses is some rich symbolic descriptions like function graphs and all. As I told you that there was problem the famous problem was solved uh, with this case-based reasoning was water faucet problem. That is a cadet. It's a company in USA, and this paper was presented in 1992 itself by Saikara. Uh, like what we do in case-based reasoning is that something like suppose what you have to is that you require a tap for your house. So your requirement is tap. Now tap how this particular reasoning we do that what class of particular of class tap you require it and all. So what it does is that in terms of function graph, we represent the entire thing. Like suppose there is a tab, then I say that okay, tab will be has some location to be installed. Then tab has needs some sort of bend also. Uh, it has some sort of say high flow, low flow, and similarly. So what we do is that your point, like your focus point is tab. Then this tab relates with location, relates with that what type of flow you require, relates that how the band is like you need some sort of curvical, straight, or something like this. So with the focal point as tab, and then I just draw a function graph where it actually talks about different locations, different type of flow, different types of band, different types of say design and all. And accordingly, by travel like one instance considerations, actually we come up with one type of tab to be uh, classified. So what this function graph actually depicts is that when you go for some sort of class of tab you are looking for, when you specify your locations, your flow, your band type, your color, or maybe then actually it actually gives it actually it actually tells you that what tab you are looking for. So the class of tab will be suggested in that case. So that was certainly the research issues. Meaning in this case, you can do some indexing based on syntactic similarity measures. Uh, there are some backtracking and adapting of additional cases always uh, welcome. There are we look for some lazy versus eager learning, because you know that dysentery and Bayesian classification, these methods are actually referred as evaluations or eager learning, I could say. And whereas just we have seen that case based and KNN, these are lazy learning methods. Now, what are differences? As I told you that lazy methods may consider query instances like some point XQ when deciding how to generalize beyond the training data D. Uh, Certainly, it cannot have already chosen global approximations when seeing the query. Whereas in case of eager learning, we actually go for global approximations while seeing the query. That is the things. Uh, as far as accuracy, Legit methods effectively uses a richer hypothesis space, because of like it actually uses many local linear functions to form the implicit global approximations to the target functions, whereas eager is actually committing to a single hypothesis that covers the entire instance space. So that actually is the difference. uh, Genetic algorithm, I'm not going through because I think you'll be doing it in the machine learning also. It's very simple. It's analogy based on biological evolution. The rule is represented in terms of string of bits, whereas you can always, any population is created consisting of randomly generated rules. Like suppose if A1 and not A2, then C2 can be encoded as 100. So similarly, you encode each of the rules based on the notion of survival of the fittest. You can actually go for new population consisting rules and their offsprings. Offsprings can be generated by crossover and mutation, which is usual genetic manipulations. So that is it. So I'm just leaving it for your self study, because you will be. I think you must be doing in machine learning also. The last method, which are the rough set approach, is actually used to approximately or roughly define the equivalent classes. Like you can see that if, for example, if you look on this, what is happening is that this is what you say that this is my class. Now, there are like this dark and this white area. So this actually the dark area which is going beyond this class is upper approximation, whereas this is uh, within this particular white area, this is going beyond compared to other area. So this is lower approximation of the C. So what you have is that our offset for a given class C is approximately by two sets. That a lower approximation. That means what you are certain to be in C. That means suppose you take any x. So if I go for lower approximation, that means this x certainly belongs to C. Whereas if I'll go for higher upper approximations, uh, suddenly I'll say that okay, this x cannot be in C. So it cannot be in C. So I'll be looking for that. The problem is that finding such minimal subsets of attributes, or what do you call it as features, is actually lined up in NP hard problem. But we can make use of discernibility matrix to reduce the computational intensity in this case. There are algorithms which actually works on or like works on this discernibility matrix as well. So this is a rough set approach. Fuzzy, very, I think it's very interesting as well. The fuzzy, you can see that what is happening in like this, that the truth values always belongs to zero, in between 0 to 1. So it actually represents the degree of membership, or some such as using fuzzy membership graph also. Like this is my, you can see that what is you have actually low, medium, and high. There are three income levels we have. So when you have attribute values, you can convert into a fuzzy values also. So we have low, medium, and high. So with fuzzy value calculated. So what is happening here is that you can see that I say that this is my low. When I go for this medium, I say this is my medium. When I say high, I'll go for high. Now the problem is that if you look for this part and this part, it's an overlapping part. Okay. So this part is overlapping part. So when any sample belongs to this part portion or this portion, then it may belongs to low, it may belongs to medium also. In this case, it may belongs to medium, it may belongs to high also. So when such uh, classifier we define, where actually we define with fuzziness, so that is referred as fuzzy set approach. So for a given new sample, more than one fuzzy value you may apply. So each applicable rule contributes a vote for membership in the categories. So typically the truth values for each predicted category are summed up. So that way it works. Okay. So this is actually the concept of fuzzy set approach. So what will next set of algorithms will talk about predictions, which we'll talk in next class. So what we have done till now is we have done that fuzzy set approach, then we have done rough set, then we have done case based, and then KNN, and then back propagations. So what we'll do, because all these are very much popular, also used in many domains, and it has utility as well. So for each of these methods, we'll be giving you like one problem uh, which is solved in nature, and then maybe set of one or two problems which is unsolved in nature, and which will be done in the tutorial part. Okay, so we'll hold it and we'll do that. Fine. So for today, uh, it's done. So we'll meet in the next class with prediction algorithms. Okay, thank you.